Now, we saw at the end of the last video that if we add this extra edge, these are the various times we would have. Now, this is certainly not ideal. For one thing, because we no longer have 6 and 7 here, we have no idea what was happening during those time steps. Also, we visited this node or this vertex twice, and that is inefficient. Now, in this example, we only have a single node that's being pointed to by 2 nodes. But if we had much more nodes being pointed by several nodes, then we see that the efficiency issue gets to become a problem. Now, we are going to solve this. We're going to make an improvement in our system to solve this. Before we make the improvement, let's see also what can happen if, say, we have another arrow. Now we have Abe being an edge among Dan's adjacencies. Okay, Abe being an adjacent vertex to Dan. And what's important about this is that now we have a loop. We're going to implement this loop by just adding this extra edge information and then see what that does when we try to run our code. Okay, and let me clear this. We are going to run our code. What's it saying? It says recursion error, maximum recursion depth exceeded. The reason why we have the infinite recursion is that at time step 1 we would be here, and as usual Abe would call DFS for Bob, and at time step 2 Bob's visit time would be at time step 2, and then as usual Dan is on Bob's list, so we visit Dan. But now Dan has a list, and the first item on its list is Abe. So it's gonna change the vertex.d for Abe from 1 to 4. And then Abe is gonna call DFS for its list again, and it's gonna call it for the first list member, which is Bob, and that's gonna overwrite 2 for the visit time with 5. And then Bob is gonna call Dan again, and that's gonna overwrite 3 with 6. And Dan is gonna call Abe again, and that's gonna overwrite 4 with 7. And that is going to go on and on endlessly. So we've seen a couple of problems with our current approach, which is that it can be inefficient because it's visiting some nodes multiple times. And also, if we have a loop, we could end up in a situation where our algorithm doesn't end at all, which is what we've just encountered. Now, how do we fix this? We fix this by noting which nodes we've already visited. Now, if you recall in the case for the binary tree, we did not have to do that because there was a sequence to how we visited nodes. We visited first the left child and then the right child, and then we were done with those children. But for a graph in general, we don't have that luxury of knowing that you can have at most 2 children. So we need another way to know which nodes we've already visited. And here's how we're going to implement that. What we're going to do is we're going to mark vertices, and we're going to mark them to know whether they have been processed or not. When we create a vertex, we are going to set it such that we know that it has not been searched through yet, hasn't been processed. And what we're going to do is within our DFS algorithm, we will only call DFS on some item on our adjacency list if it has not already been processed. Okay. And whenever we encounter a vertex for the first time, we will change its condition to show that it has been processed. That is, we've met it before. Okay. So that we don't repeatedly process the same vertex. And that is it. If we execute this, now we are going to... Okay, now obviously we've solved the infinite recursion problem. Okay, and now let's go through our algorithm and see what's happening. We are calling DFS on the AB vertex, and we are going to take it that if a node hasn't been processed yet, it is white. Okay, and if it has been processed, we will put a red color within it. And when we call DFS on the VAB vertex, we change it to red to show that it has been processed. Okay, and we put a timestamp of 1, and then we call DFS on its first neighbor, which is Bob, and we put a timestamp of 2, and we show that it has been processed. And then we call DFS on Bob's neighbor on its adjacency list, which is done, and we put a 3 beside and show that it has been processed. And then Dan will, because it's got a list, will get here, and if neighbor is processed, or if it's not processed, it would call DFS on its neighbor. But because list node Abe has been processed, it doesn't. Okay, and Dan doesn't have any other neighbors, so we update its final time to 4, and we backtrack. We put a 5 here, and Abe still has other items on its list, so it's gonna put a 6 beside Eve, and Eve doesn't have any items on its list, so put its finish time at 7, and then Abe still has another item on its list, so we go to Cass, 8, and Cass has an item on its list, which is Eve. By the way, when we get to Eve, we would have marked it as having been processed. So Cass will see that Eve has been processed, and then it will go on to the next item, which is Flo. And so, by the way, Cass would have been marked as processed. Flo would be 9, and Flo's doesn't have anything on its list. It would be marked as being processed. Its end time would be 10, and then we backtrack. We put an 11 here, and then a 12. So no node has been visited more than once, and all of the times have been accounted for. And we did this by having this indicator, okay, and keeping this information on whether a node has been visited before.